In this video, we're going to explore exponential functions and just see how they might differ a bit from or a lot from the linear functions we have been working with, even from power functions. So exponentials, they'll start off slowly and then they'll go up really fast and they'll beat out any power functions in the long run. So here we have a research experiment, and the scientists established a colony of 100 fruit flies. So that's the initial value, okay, at day 0. That's important to note, that the day is 0. And determine that the colony triples every day. So it increases by a rate of 300%. So with exponentials, we're looking at a rate of increase rather than like just goes up by 2 every time, like with a linear. So we would start off with the number of flies is 100. Then I'm going to increase that up, triple it. So the next day it goes up to 300. So if we kind of see a little pattern happening here, then we'd have 900. And you can go ahead and fill in the rest of the pattern there. You can pause this at any time, kind of doing along with me, a little ahead of me. And they'll break down to prime factors. Like if I actually broke this down, this would be 100 times a factor of 3 to the 0. So that's my initial amount. So anything to the 0 is 1, just remember. And then this would be 100 times a power of 3 times to the power of 1. And then this would be 100 times 3 to the power of 2, and so on and so forth. So go ahead and pause and fill in the rest. And then once you do that, so that'll be classwork, and then go ahead and plot. So as classwork, we want to plot the points on this little graph here and see what that looks like. Okay, so we have our number of flies is F, our exponent is D. And we're kind of thinking of this same pattern that I used above here to kind of track what our equation might be. And you might think of, can you find the equation? Can you figure out, based on this pattern here, what an equation might be that you could set up? So go ahead and just try that. If not, come back and check. Okay, so I've gotten my graph done. It starts off slowly and moves up. Hopefully you also had these numbers here, the 2700 and 8100 for the last bits of it, of the tail end of the table. And then we have our form, which is f of x, or y, you could say, equals a times b to the x. So for these, our variable is the exponent. So that's a difference between having it just be like 3 squared or something like that. Our exponent is going to vary for exponential functions. And then once we go ahead and look at this, the initial value is our a, our coefficient, to the base with the exponent. And I make sure I declared my variables. And I also have my base, which is the rate of increase or decrease. Now this one is at triple, so you could think it increases 300% each time, or as a decimal, 300% is 3. And the d, we're just going to leave as the exponent as the variable. Okay, for this next one, number 2, I want you to try to do as a classwork. So I'll start you off though. After 100 milligrams of medication is given intravenously, the amount remaining in the body decreases by 10% every hour. So that's 90% would be remaining the first hour, then take another 90% off, right, each time. So that would then be 81 in the second hour, and you can see that's going to be 100 times 2 factors of 0.9. Now be careful, the common mistake is people will just put 0.1 in there for the base, but you have to think it's 100% minus 10% gives me 90%, convert to decimal is 0.9. All these functions here are going to have your base be as a decimal, not the actual percent form. So remember to shift that around. So see if you can figure out the remaining values there in the table, and then you're going to graph it down here just like we did before. The scale's a little bit different though, so it might look funny. So I gave you some tips on, like, is it linear? Is it exponential? How can you tell for sure? And then see if you can come up with an equation for that on your own. Remember to declare your variables here. They're kind of listed here, but it's always good practice to do that. And then we'll graph it in Desmos and see what it looks like. So just go ahead and pause and complete that up. Okay, so here's the answers. I filled in the rest of the table. Notice the pattern. You're multiplying by factors of 0.9 each time. We talked about this base and how that works. Plugging in those points, we get something that almost looks linear if I especially stretch it out. So be aware of that when you're zooming. The formula here, or equation, I should say, function, declare my variables, and I get m of h equals 100 times 0.9 to the h. And I just put this note here for in general so you can track. You might want to, write that on a separate piece. But f of x equals a b to the x, where a is always the initial value we start with. And then we have b is the growth rate or decay rate for every increase in x, which is our variable exponent. Here's a graph of that in Desmos, 100 times 0.9 to the x. The other one that we did earlier, just to show you, it's a little harder to see easily, but because it's tripling, so it's pretty big. So we'll put that one in there too, but you can kind of see how it goes up, but it just looks a little odd, like it's almost like kind of square it off a little bit. So you can see where there would be deceiving depending on how you blow things up or shrink things down with using technology. So just be aware of that. And I think that is it for this video. So we'll wrap up there and have a great day. We'll look for some more parts on this one to come.